you on a few health and safety items. We're not expecting any fire alarm today. If you are here in a continuous well, please just evacuate the room the way you came in, and there is an extra exit here that you can use. The nearest fire alarm assembling point is across the main road just outside the cathedral. Right, so today the session will be live streamed and recorded, and there will be a drink reception after the whole session. We're gathered here today to celebrate another milestone of our colleague, Professor Simon Maskell. So the award of Royal Academy of Engineering Chair in Information Fusion, funded by Defence Science and Technology Laboratory, Dstl. People in the room know Simon in various capacities: friends, students, colleagues, and collaborators. And tonight, I'd like to take a moment to reintroduce Simon to all of us. Professor Simon Maskell received his Master in Engineering from the University of Cambridge in 1999, followed by a PhD in Engineering in the same university in 2003. After that, Simon spent about a decade working for Kinetic, a British defense and security company where Simon was a senior fellow, leading a team of about 135 professions, including all sorts of engineers, mathematicians, statisticians, computer scientists, physicists, and psychologists. In early 2013, Simon made the very rare move straight from industry to university, joining the University of Liverpool as the Professor of Autonomous Systems. EEE, as the host department, takes great pride in this appointment. And I believe one of our former heads of departments, Professor Jason Rolfe, who unfortunately couldn't join us today, should take credit for that. For over 20 years, Simon and his teams have led a pioneering work in what we now call big data, before this term was widely used. Their research produces innovative solutions to some of the most complex challenges in the nation and globally, such as developing systems for defense intelligence to automating risk assessment for satellites and health regulators, just to name a few. Their work, importantly, translates vast and complex raw data into valuable insights that support important decision makings and in many cases save lives. They have visibility and success both inside Liverpool and outside. Many of us know Simon as a star in his field, a research leader and an entrepreneur. But I'd like to flag another contribution of Simon's that was not very often being mentioned, and that is education in the university. In 2019, Simon set up the EPSRC Center for Doctoral Training in Distributed Algorithms in collaboration with STFC Hatchery, IBM Research, Allen Turing Institute, and another more than 20 project partners. Through this CDT, they are training over 60 PhD students to meet the urgent national demand in highly trained data engineering. Even to this date, Simon continued to contribute heavily in teaching a module in our second year called Instrumentation and Control System. And this module has more than 250 EEE students sitting onto it every year. Many in this room today have been taught, mentored, supervised, and supported by Simon in all sorts of ways over the years. It is an absolute pleasure for EEE to host Simon's inaugural lecture tonight as he shares his journey behind this award and his thoughts for the future. Before I invite Simon onto the stage, in just 2 seconds, I'd like to remind all that there will be a Q&A session chaired by the University Provost, Professor Richard Like, at the end of the lecture. If you could please save all your questions for the end. And now, ladies and gentlemen, please help me welcome our speaker tonight, Professor Simon Maskell.
Gosh. First off, thank you for coming. It's a pleasure to see you all, and thank you also to those who are online for attending, particularly those who are on other sides of large stretches of water, called the Atlantic, for example. Thank you very much. So I'm going to try and give you a talk, as Wenqing kindly introduces, about how we got here, where here is, and what comes next. Right. So it's 2025, and as Wenqing highlights, I've been at the University of Liverpool since about well, not exactly since 2013. Prior to that, I worked at Kinetic. And prior to 1999, I was doing a master's at Cambridge, integrated masters. So I actually did my PhD. So I should say, when you get, you look up what an inaugural talk is supposed to be, there's an implication that it's about launching something, and the audience is likely to be quite varied, which is good. So I'm going to try to teach you all a little something. That's my objective. I will see if I succeed. There are some people in the room who know an awful lot about the stuff that I've done and how it's done and how it works. There are some people that are probably new faces. Thank you for coming. And hopefully I can tell you something about my background that you weren't, all of you weren't aware of. So one such atom of information is that my PhD was actually funded by a thing called the Royal Commission for the Exhibition of 1851. So when the Great Exhibition of 1851 happened in London, they made some money. They bought some farmland outside London, which is now called Kensington, and they rent out that farmland to Imperial College, Royal Albert Hall, and so on, and they reinvest that rent in people who they ask to make a difference. That's their sole purpose. Yeah? So you write a complicated proposal, they assess it very rigorously, and then they say, don't care whether you succeed in doing that, but make a difference. That's their mantra. But anyway, that paid for a PhD that actually ran concurrently with my first few years at Kinetic. Whilst I was at Kinetic, this will become... Well, let's take a tiny step back. One of the things I took away from the engineering degree I did was the connectivity between different topics. So the idea that electrostatics and fluid mechanics might be driven by the same mathematics makes me think, hold on, if I can be better at that maths, I can apply it in these two completely different areas. Or turn it the other way around, if I can be good at two totally different things, it might contribute to something that other people might find difficult to access. So one specific thing that came out, here we go, as a result of that kind of mindset is that, as some of you will be aware, I work on something called tracking quite a lot. I'll explain what that is in a minute for those who aren't aware. At least at the time, there were lots and lots of people trying to sell, in some senses succeeding, what I think of as cathedral-esque solutions to the problem. So company one, apologies, company one, builds a system that solves a problem. Company two, apologies, company two, goes and builds a solution to a similar problem. And then you can't kind of flex. There's no ability to say, well, what would happen if I had the first half of company one's solution with the second half of company's two solution? And the reason that comes about, I perceive, is because the fact that the mathematics is modular gets lost in translation to the object-oriented software design. But actually, modularity in maths and modularity in software is the same idea. You just have to think it's the same idea. And then you can translate the ability to calculate integrals in lots of different ways into a component that you can plug in into some framework. Now, I was actually motivated by the fact that my annoying boss at the time, who was excellent, kept on coming at me with these annoying things called data sets, and I just wanted to get him out the office. So I made some software that made it easy for me to quickly analyze data sets, apply a whole raft of different algorithms, and apply it to any one of these arbitrary data sets and get Neil out the office. That got given a name because of where I was at the time, which was Pint. I needed a name quickly. I had to reverse engineer an acronym, and the reverse engineered acronym, with a slight nod to Unix, was Pint is not a tracker. Pint's not a tracker is Pint is not a tracker. It turns out that in about the year 2000, some people came up with a thing called Pint, which has a logo. So I'm not aware, where's Paul? Do we have a logo? I don't remember us having a logo. Okay, well, yeah, so anyway, there is a Pint on the internet with a logo, which ironically relates to timing. Now that has subsequently led to the formation of a company wearing a slightly different hat called Voyant. And Voyant is a spin out from the university that seeks, so no, no, not quite yet. Hold on, sorry, wrong bit. Let's put the University of Liverpool hat on. As part of the University of Liverpool, we have developed components within a framework that's been led by Dstl called Stone Soup. Stone Soup embodies the same principles as Pint did, but it converts that from being a bit of software that a company called Kinetic at that stage was using for its own internal purposes into an open source tool. What's happened subsequently, sorry, select that now, is that the university has spun out a company called Voyant, which seeks to take that mindset and specific embodiments of technology that we have developed at Liverpool, one of which we'll talk about in a minute, and turn it into something that people can use. Rather unsurprisingly, in this journey, there has been extremely significant investment from both the UKRI and Dstl. And I should overtly thank both organisations and their representatives for the support that I've received over the last couple of decades. But also, more recently, the Royal Academy of Engineering, and wider Ministry of Defence, and the companies which are represented today, and bits of government that are in the room and or online, and are heavily engaged in trying to take this technology forwards in a defence and security context. But the technology that I have focused on developing over the preceding few years is general purpose, and I'll explain what the generic nature of the purpose is in a minute. But there are then other niches where one can apply the same technology, and one specific other niche is in insurance. So when we were at Kinetic, we worked on what we now call data science and AI, and specifically we looked at helping insurers understand the risk posed initially to satellites. So when you buy car insurance, let's say, what happens is that the insurer looks for people living roughly where you live, with roughly your job, with roughly your age, figures out how many of them claimed last year and what they paid, or what the insurer paid, and from that calculates your insurance. If you adopt that same principle for satellites, basically all satellites have the same insurance premium, which is really bad news because some satellites are a bit dodgy and some satellites are engineered really, really carefully. And so you can't have any price differential in your insurance. And therefore, you end up insuring some high risk assets and some low risk assets. If you could accurately perceive the risk that a specific satellite experiences, you could price the insurance of a low risk satellite under the market, because you're the only people that know what the true market risk is, and you can walk away from all those risky satellites. And so a company called Schemas, led by Andre in the room, was set up, and we at Kinetic supported that. That has evolved in recent months and years to another hat that I'll wear called Intellegri. So similar idea, different specific. What we want to do here is to assess risk to fully understand the capital requirements that an insurance company needs. So it transpires that this same mathematics that can understand the risk posed to an individual satellite gives you a really good handle on the risk posed to a portfolio of things you're insuring. So the correlations between if one thing claims and another doesn't, how does that all get manifest, is fundamentally the same mathematics. Technically a spin in from the university was formed in the last 12 months called Intellegri, and we're really, really excited about how that will grow outside of the defence and security context. And that's not it. So there are also people represented in the room and online from a number of organisations. So thank you if you can see your logo, and apologies if you can't, who have all contributed to the work that we've been doing over the last few years. Many of those companies are in a defence and security context, but several of them are not. And that ability to take ideas, mathematical ideas, and apply them in different contexts is, I think, that, or the adaptability that stems from that is what I perceive to have underpinned the successes we have had. And I shouldn't forget that I feel a very strong affinity to Liverpool as a city and a region, and I really want to ensure that the work we do here, be it part of the university, part of Voyant, part of Intellegri, is grounded in this great city. And I feel very passionately about that, and I'm really pleased at the engagement we've recently been having with the combined authority. 2018 turns out to be a pertinent year because it turns out that's when I did my first inaugural lecture. So this is actually a sequel, which is why it says Inaugural Strikes Back at the top. That's a kind of reference to a decent film sequel, of which there are fewer than I would like. But I haven't got a fancy hat, but I have got some baseball caps. So what I took the remit for this inaugural talk to be is to kind of take the time since 2018 to now and try to say what's happened in that 7-year period. Where are we now, and where does that take us in the future? But to do that, we need to understand what is it that I do. Yeah? And so here's an example of something that I've worked on over the last few years, since 2018. So you may recall that early 2020, COVID hit, and I looked across my peers, and I saw lots of people trying to calculate the parameters of the virus to more significant figures than the last person. That's kind of fine, but what you want is not an accurate perception of, or a best estimate of what is going on with COVID. What you really want is you want to be able to balance the negative and positive impacts from decisions that you need to make. So what matters is not your best estimate, but deciding, and specifically deciding whether to lock down the UK. And what we need to know to decide whether to lock down the UK is whether the R number is above 1 or below 1. If it's above 1, the virus is growing, more people are going to be infected with time, we have to intervene. If the R number is below 1, we can stand fast and the virus will eventually decay to not being there anymore. And so we need to know about the R number, but we don't know it precisely. We have some data, and the data comes from, let's say, hospital admissions, ONS data about deaths, and in fact we used data from 111 calls. And so what we want to do is to combine that data to figure out what do we know about the R number, and if we can figure out which side of 1 the R number is, then we can tell Boris what to do. Yep. If you look at a paper that was written by some Dstl colleagues on how to combine the estimates that different teams, including us, produced estimating the R number, what you find, so this vertical axis is R number estimate at 2 different dates. The dots are your best estimate of the R number as calculated by a team. The error bars, the lines, are how uncertain these different teams are. So the main point I want to make is that the variation in how uncertain people are about the R number is very pronounced, and that some teams, let's pick this one and this one, are extremely confident about totally different conclusions about what the R number is. So this team thinks the R number is definitely above 1. We should definitely lock down. This team thinks the R number is definitely below 1. We should just leave it and it will be fine. It's really worrying to me that we can have eminent scientists being extremely confident about totally contradictory conclusions. The thing we really need to do is to make sure we understand those error bars. If we understand the error bars, we can inform decisions. If we can inform decisions well, then things will be as good as they can be, albeit there's a global pandemic going on. So this is really important to balance the risk that stems from misperception, in this case, of what the R number might be. So that's one example. We, as the university, developed a model. That model was used by UK government to inform the R number for a year and a bit until it got all of them got turned off. Another project that has been ongoing for a while that some of you will be aware of is that there was an aeroplane, MH370, that back in 2014 went missing, took off from Kuala Lumpur, headed for Beijing, and essentially went off radar. That annoying Australian now, Neil, is now, or was at that point, leading the the guy that was coming down the corridor with data, was leading the work in Australia to figure out where to look for MH370. He sent me an email one day. It turned out I had an all-day meeting that day, which was cancelled. And so I very carefully reviewed the maths that the Australian government was using to figure out where MH370 was, and that informed the first search for the aeroplane. Subsequently, I've got drawn into various discussions with the Australians and a company called Ocean Infinity, trying to figure out where should we look. And again, accurately reflecting the uncertainty around where MH370 might be is critical if you want to find it. Yeah, knowing where it might be and then being very confident about something that turns out to be wrong is pretty useless. So we've been using data from a satellite system called Inmarsat and other sources of data to figure out where MH370 might be. And that's a picture of me in Malaysia early this year, helping to convince the Malaysian government to do a search, which was started relatively recently, but has taken a break due to the rather extremely grim weather that occurs in the southern Indian Ocean at this time of year. So my point is that there is a generic problem, and I've got kind of two equations. So we'll try and walk you through this one. We have a decision to make. Yeah, we want to decide something. We'll call the decision D in red, so that might be where to look or whether to lock down. We argmax D, that means we pick the best decision, which, and this is an integral, so this means which we average over what might happen, and we average over X. So we average over all the different places MH370 might be, or all the different R numbers that might exist. And for each value of where MH370 might be, or what the R number is, we have two quantities. One is how likely we think it is, or probable, technically, sorry. So given the data Y, what this means is how probable is it that MH370 is there, given the Inmarsat data that I have. And then a second term, which is how useful would it be if I made this decision if that was the case? So I have these two concepts. How important is it that I do something, and how likely is it that I'm in that scenario? And we average that over all the different scenarios that might be true, and that enables us to come up with the best decision. But the point I'm trying to make is that the averaging needs to be based on a really accurate perception of what the uncertainty is. If we misperceive the uncertainty, we're in trouble. And so the focus really for the research that I have done and do is around characterizing what this uncertainty is. And that's a generic problem that you can lift up and apply, be it in a sonar context, an insurance context, a COVID context, or an MH370 context. And it is generic. Yeah. And this is a word that gets used, but I think people often struggle to understand what it means. So when you say generic, people perhaps don't understand it, but the point really is that it applies to large numbers of specifics. So it's the same maths for COVID, it's the same maths for MH370, it's the same maths for a radar system, it's the same maths for insurance. And the maths, if we can package the maths in a way that enables it to be morphed to the particular problem, the maths has longevity beyond the specific problem. You can lift up the advances you make in one context and apply them in the next, and the next, and the next, and the next. And that enables you to make progress. I couldn't resist also putting in this one, which you might have thought was coming, as you know, which just says that what you believe is related to two things. One is your prior knowledge, and the other is how likely the data is given that the scenario you're in. The point being, you've got a balance between the information you have from data and your prior assumptions. The stronger you make your assumptions, the less reliance you need on the data, or put another way, the better inferences you can make from the data. And so you want to try to empower the analysis with as much prior knowledge as you can get, but whilst also respecting the fact that you've got to fit the data in some sense. But there's an elephant in the room. Right, and this on the right is a relatively well-used picture of, if you ask ChatGPT for a picture of a room with absolutely no elephants in it, that's what you get. And that's the state of the art, albeit on ChatGPT, which is arguably the tip-top technique, but there we go, in 2025. Rewind to 1998. So 1998, may recall, I was an undergraduate student at that point, and I actually did a project on what at that point was called voice morphing, what we call deep fakes now. So I was working on essentially deep fakes in 1998 as an undergraduate. Didn't work like many undergraduate projects, but it kind of hinted at what might work. Fast forward 10 years. So at this point, I'm now working for Kinetic in Malvern. It turns out that other people down the corridor were working on things that they would call what was that? Componential coding and AceNet, I think was what Steve would have called it. And those techniques actually were deep learning, but the individuals who were doing the research failed, arguably, to convert their insights into something which could actually be a commercial advantage. In 2008, I then went to a DARPA workshop in DC as one of two people from the UK, and I tried to argue that what we really need is something that strikes a balance between using the data, which deep learning and AI and machine learning are really good at, but also using your prior knowledge. Yeah. The other people I was arguing against included Andrew Ng, Yoshua Bengio, and Yann LeCun, so godfathers of AI. They arguably won the argument, so they certainly got funding in the short term from DARPA. But my real point is, whilst they went on to lead to the development of AlphaGo and then the technologies that that lead to ChatGPT and so on, I still remain passionate, despite it being back in 2008 that I was making the argument, that we really need to strike this balance between data-driven technologies and technologies that are informed by prior knowledge and can really fully capitalize on the data that we have. Now, when data is really numerous, this probably doesn't matter. So if you download a few more billion images from the internet and retrain your model, you can probably get away without any strong prior knowledge. But if you want to do things, particularly in contexts like insurance, defense, security, but also manufacturing and health, where data is typically expensive, and saying, can I just have 10 times as many people who've caught cancer, please? That's really not acceptable. We really want to fully capitalize on the prior knowledge that we have. And so that's been running at the back of my mind. At the same time, it's worth emphasizing that the machine learning and AI world is capitalizing on bigger and bigger computers, and to quite an incredible degree. So you may or may not be aware, in about, let's say, 2013, the speed of an individual processor essentially plateaued. So after 2013, no one processor is going to go that much faster than any other processor. But what happened is people invented dual core processors and quad core processors and GPUs and larger and larger and larger computers. And so Moore's law, this doubling of compute capacity every 18 months, became increasingly delivered by many core architectures. That's a technology-driven development. What's happened subsequently is that commercial ambition has taken over from engineering and scientific advance, such that now the compute power that's thrown at training these deep learning algorithms doubles every 4 months. So that's an 8-fold increase in computing every year that we have access to. So if we don't get on that train, the train is leaving at a rate that is doubling every multiplied by 8 every year. So we've really got to embrace this ability to have big computers, but also do so in a way that capitalizes on prior knowledge. Whilst at Kinetic, I had sales targets, at various points, and I therefore went on various training courses. One of those training courses was called High Value Selling. The thing it taught me is that if you sell a commodity, the person that sells the commodity for the cheapest price wins the deal, yeah, because it's a commodity. So if everybody has the same thing, people buy the one that's cheapest. So selling commodities sucks. What you want to do instead is be super sharp about what it is that differentiates what you have relative to everybody else. If you can be really clear about that, then you can price your commercial offer, your research, whatever it is, and do so in a way that commands a price rather than being a desire to drive down your cost base and therefore be able to offer something that's cheap. So the salesman, at least the training as being a salesman that I had, really focuses me on having a differentiated offering. As I said before, I'm interested in tracking. So what does tracking mean? It means taking data, for example, on the left-hand side, zoom in, no. So imagine you've got a planet, you've got lots of ships on the planet, the ships each maybe transmit their position, which they do, and you want to collate all that information, but you also want to combine it with, for example, satellites that can see there's a ship here. How do we bring that all together, given that there's this stream of data coming in? Joining the dots is a way of understanding it. You can apply the same techniques to, for example, telescopes and radars looking at debris flying around the planet, which is the picture on the right. But to bring that to life a bit, here are 4 photos of the team that I've been working with at various different points in time at Liverpool, and it's just worth highlighting this. I think Wenqing has hinted, some of the people on the left-hand side are sat in the audience and are still University of Liverpool people, but many have gone on to other things. Tracking, and are still here, come today, for which I'm obviously really grateful, but tracking is the problem of figuring out which person in which of those photos is the same one. So you can probably make out, I have actually changed my trousers, don't worry, but which one is me in those 4 photos. So a potential differentiated offering that we, the UK, are particularly good at is something called particle filters. So at a super high level, what you do when you want to follow something, so let's assume you have a sequence of positions from, let's say, some satellite images of a ship, and you want to figure out what the velocity of that ship is. So you could just join the dots and say that the velocity is the difference between the 2 dots divided by time, but the dots are typically noisy, and so you need to be able to do that in a way that respects the noise. And you might also have lots of dots, so you don't actually know, is this the same ship as that? And it might be advantageous, in fact, to be able to consider lots of candidate places where the ship you're interested in might be. So what we do is we guess. Yeah, we throw down guesses, and we call those particles, which is why we call it a particle filter. We look at the data, and each guess predicts the data to some degree. Some guesses are good, some guesses are less good, and we give the particle a weight corresponding to how good it is at predicting the data. So the ones that do well, we give a high weight. The ones that do less well, we give a low weight. And then we with the guesses that do well, we congratulate them, and we make copies of them. The ones that do less well, we kill off, and we do that in a way that means the statistics work, so it's stochastic. And it turns out that this is really great for specific applications. So one would be if we have a very weak signal which makes it very difficult to know which of the artifacts in the data are those that relate to the objects, and is there an object there at all? Now, if you adopt this approach and you adopt it in the context of, let's say, a radar or a camera or so maybe a camera looking at an aeroplane, an acoustic sensor, it is frequently the case that your improvement in performance is of order 6 decibels. Yeah. So what that means in real numbers is that you've been able to process the data from a pre-existing sensor in a way that emulates a sensor that might have been 4 times more expensive than the sensor you already have. So you can then start pricing your advance, possibly, certainly realizing that the sensor that would have had to have been built to achieve that same level of performance enhancement would be astronomically more expensive, and that gives you a differentiated offering that you can then seek to benefit from. You can get a similar benefit, it turns out, because you guess. Your guesses can describe whatever awkward geometry you like. So if you imagine that you had a radar, let's say, and the radar measures the range to something very accurately, it kind of describes a banana in space. And the banana is something that you can describe by putting lots of guesses along the length of the banana. And if another radar in another place gives you a second range from its location, you can describe the intersection of these two banana, or technically contact lens shaped objects. And it turns out that enables you to really localize in on where these two geometries intersect with one another. So you can get very accurate perceptions as to where an object is, which matters if you work in certain contexts. So particle filters, in general, are something that the UK has done a lot of work on, and they were often claimed to be paralysable. Okay, so paralysable means, in theory, somebody else could turn this into something which could be implemented in parallel. That's what paralysable means. What we wanted to do was to have something that wasn't paralysable, was paralysed, was actually an implementation that could run in parallel, could exploit the technology that's being developed for deep learning and AI, and therefore deliver performance benefits that these particle filters would be able to achieve. So when you teach, or when I teach, I acknowledge there are some people in the audience who are going to try to scrape a third, and there are some people in the audience who want to get a really high first. Okay, and you need to give some people in the audience who are finding this all a bit alien, aren't quite sure what that guy at the front's talking about. You need to give them something to grab hold of, but you also need to feed the people who are aspiring for the high flying first. So I'm going to attempt to do that with you. So this, for those of you aiming for the third, right? Imagine that we have a list of numbers 2, 3, 4, 3, 1, 5, 4, and 4, and we want to add them up. Okay, so we could get our calculator out, and as one person adding up 2 plus 3 plus 4 plus 3 plus 1 plus 5 plus 4 plus 4, I'm confident that you would all be able to work out 26. Okay. And that takes you as long as it takes you to type in those 8 numbers. Okay, so if I doubled the length of the list of numbers, it would take you twice as long. Okay? I'd like to do it faster. Let's assume I've got 8 students, and I would like to do it faster than typing the numbers one by one. So what I do is I get some students, so 4 students in this case actually, and I ask one student, add together the first 2 numbers. Second student, add together the second two numbers. Add together. Ooh, hello. Okay, fast forward. Recap. I've worked in lots of places. I've done stuff. Bayes is important. You need to sell things. I've worked with great people. Particle filters are good. To add up numbers, you put them in pairs. That's the short version. We then take the pairs and we add up pairs of pairs. And then we take the pairs of pairs and we add up the pairs of pairs. And so we work in this tree. Yeah? And so hopefully you can all see that if we had 4 students, we could do that in 3 steps. Add up the pairs, add up the pairs of pairs, add up the pairs of pairs. And 3 is less than 8. But crucially, if I doubled the number of data, I would just add 1 to how much time it would take. Everybody happy with that? Maybe not happy with that. That's a teaching trick. Okay, now so well done on the third. Now to get a 2-2, imagine that we want to work out the cumulative sum of these numbers. So the cumulative sum is the sum of all the numbers to the left of a given number. So the sum of all the numbers to the left of 2 is 0. The sum of the numbers all to the left of this 3 is 2. The sum of the numbers all to the left of the 4 is 2 plus 3 is 5. 9 is 2 plus 3 plus 4 plus 3. 12 is 9 is 2 plus 3 plus 4. Sorry, 12 is 2 plus 3 plus 4 plus 3. So you're adding up the numbers. So to work out a cumulative sum, we start on the left-hand side. We say add 2, then add 3, then add 4, then add, so you walk along. And we can do that in a length of time that scales with our calculator, walking from left to right. Okay. There is a textbook algorithm called prefix sum, hence 2-2, that you can use to calculate that in parallel. So the trick is that you take 0 at the top, and then on the left-hand side, you copy the number at the top down and to the left. And on the right-hand side, you take the number above and the red number on the left, and you add them together. So 0 plus 12 equals 12. Yep. And you repeat that process. 0 goes down here. 0 plus 5 is 5. Here, 12 goes down. 12, this 12 plus that 6 is 18. So there's a process that you go through, and you do that, and you walk down, you do the same thing along the bottom. And so perhaps surprisingly, you can calculate these cumulative sums by just walking along the list. So rather than walking along the list, you walk up a tree and down a tree. Yep. And because the tree is a so-called binary tree, we can do that fast. And we can therefore exploit hardware to be able to calculate cumulative sums efficiently. But nobody cares about cumulative sums. People might care about particle filters. So here's a problem that crops up in particle filters. I've got 8 letters of the alphabet: A, B, C, D, E, F, G, and H. Sorry, this is 2-1 territory now, okay? And I would like to make 1 copy of the letter B, 4 copies of D, 1 copy of E, and 2 copies of G. And the numbers might differ, but they add up to 8. And I would like to do that. So here's an example of the result. So 1 B, 4 Ds, followed by 1 E and 2 Gs. So you can think of this as a routing problem. I've got the 8 letters of the alphabet, and I want to be able to route them, through such that I can quickly end up with the workload distributed across my computers in this case. So what I do is I give them all a number, 0 to 7, and I then count up how many zeros there are to the left of each number. So to the left of this number 1, there's 1, 0. Sorry. To the left of this 0, there's 1, 0. To the left of this 4, there are 2 zeros. To the left of this 1, there are 2 zeros. To the left of this 2, there are 3 zeros. This one, and this one. I can do that using the cumulative sum thing I've just taught you about. Yeah, I can do it fast. That tells me how far I want to move things so they all would be bunched up on the left-hand side. Yeah. So if I were able to move things that distance, I would have B, D, E, and G all on the left-hand side of my list of numbers. Okay. So my strategy, first step of the strategy, is push everything to the left. Okay. So push everything to the left. The second step of my strategy is figure out how much room I need to make room for the copies I want to generate. So to calculate that, what I do is I work out the cumulative sum of these numbers in red with the numbers below in orange, and then what I do is I subtract the number at the top, and I end up with these numbers here. But what this means is that I want to move this element E 3 to the right. I want to move this one 3 to the right, this one 4 to the right, this one 3, 2, 1. If I do that, I make space. So my strategy is push to the left, make space. Once I've made space, I can then populate the gaps with the elements, in this case, 4Ds. So just recap, start with a list of numbers that add up to 8, push them all to the left, make space, and then populate the gaps. Okay? Congratulations, 2-1, right? Now, for you who want to get a first, we'll now look at the detail of how you do those steps quickly, because you're all very capable students. So to move things to the left by an amount that we've calculated, what we do is we represent the distance we want to move in at a binary number. So we think of 1 as 1 plus 0 plus 0. We think of 2 as 0 plus 2 plus 0. We think of 3 as 1 plus 2. So for 7, it would have been 1 plus 2 plus 4. And then we look at that binary encoding, and we start with the biggest number, the one at the bottom, and we move, and we notice that we don't need. No, sorry, I got that wrong. Yeah, we start the one at the top. Sorry, wrong one. Almost lost my first there. So we look at the one at the top, and we move anything that has a 1 here, we move 1 rung to the left. We then look at the second row. Anything that's got a 2, we move 2 rungs to the left. And anything that had a 4, we would move 4 rungs to the left. So by encoding the shift in a binary pattern, it turns out that you can do this super fast. You can do the same thing for shifting things to the right, but you have to use the most significant bit first rather than the least significant bit. And you can also use the similar tactic for populating the gaps. Why am I telling you this? Because that is what we patented. Yeah, that is the patent that we got that gives a monopoly on how to do that resampling step within a particle filter, and is the premise of both Voyant and Interlegri's ability to have a discriminated offering relative to the marketplace. So hence, right, Voyant and Interlegri, but also other things that we are looking at. So calibrating agent-based models, it gives us a tool that may or may not turn out to be handy, but certainly means that we can really do things in that space. But it also enables us to tackle problems involving decision trees, which happen to be really popular algorithms to use in a health context, but also in a security context, and also enables us to empower languages for solving these Bayesian problems really well, an example of which is Stan. So having that patent gives the University of Liverpool, in my view, and therefore the partners represented in the room, an ability to tackle problems that nobody else is going to be able to do. But also, it tells us that there is a skill set that we can develop. And this was the premise of the CDT that was mentioned a few moments ago, which is that if we can empower people with an understanding of the data science techniques and an understanding of the computer science, we can really have people who can develop patents like that. So not only can we have the patent, we can make people unicorns in the distributed algorithm CDT who can go on to create their own patented techniques and go on to great things. So that's kind of the up to now, and there's a logic about how to take that forwards incrementally. Yeah? The purpose, as I see it, of the Royal Academy of Engineering Chair is to go back and say, right, that's all very well and good, but let's develop the next rung of technology, the next big steps forwards. And there are some specific things that we're looking at in that context. So one is about distributed proactive decision making. So imagine you've got lots and lots of sensor systems. They're all communicating with one another. They're all anticipating the future and mitigating what might happen by acting now in a way that respects the fact that the future is uncertain and we don't even know what the current state of play is. We also want to understand what we don't understand, which it turns out machine learning people find really difficult to get their head around. But that should enable us to be confident about what we're confident about. Bit Rumsfeldian, but never mind. And then also we would like to be able to have prior knowledge that incorporates the ability of the people that we're up against being intelligent and deploying, for example, deception to try and throw us off the scent. So that's what I see as the breakthroughs of tomorrow that I'd be coming to report if I were unfortunate enough to need to do a third inaugural lecture at some point in the future. I don't know, return of the inaugural lecture or something. So two closing remarks and two sets of people I want to thank, really. So I should also be clear. Thank you to the people that have helped organise today and everything else that goes on around me at Liverpool. It's absolutely brilliant to have you around. So thank you enormously. My PhD supervisor was Bill Fitzgerald. He is no longer with us. He was a brilliant man, and the group he created at Cambridge, Signal Processing Group, from that, 10 years before I left, there was a guy called Mike Lynch who created Autonomy, and it was a production line of really effective spin-outs that really went and transformed the world that existed at that time. If I could be anything like the group that he had and created, I would be immensely proud. Sorry, slightly emotional. The other thing I'm proud of, unfortunately, again, not here today, is my family. Toby is as photogenic as I am. He's the one looking away from the camera. Leo in the middle, Michelle on the left-hand side. And amusingly, I don't know how many of you recognise that the backdrop, that's actually round the corner from RAF Findingdales. So it's on the Yorkshire Moors, just down the road from there. So thank you to them, but thank you also to you. I hope you found that illuminating and learnt at least something from the preceding approximately 45 minutes. Thank you very much.
Both. Thank you, Simon, and thank you in particular for aiming at least some of that lecture at people like me who would have got a third in maths at the absolute most. We are supposed to move on actually right now to a reception outside, but I think we should have the promised Q&A. I realise that's keeping you from a drink, but let's open it up to the audience who would like to ask. I've got a question there, and we've got to have a roving mic. Please use that so that our online listeners can also hear.
Thank you, Professor. So it's not very familiar, so Gene's data that the question about that saying that disappeared. So I presume it's the younger way of reaching.
I calculated there was a 20% chance they would have found it in the search they did most recently up to now, and they did not find it in that time. So no, yes.
That's
Yeah.
So given your knowledge, I guess, of defence and untoward actors, perhaps trying to hide information, why do you think it's taking so long to find the plane?
So that's actually relatively easy. I don't think it's the deception coming in. I think it's much more to do with the fact that the ocean is enormous. So the area they've been trying to search in is approximately the size of the UK. So if you imagine trying to find one plane by driving a UAV around, looking down, it's a very big place. And they've looked in that area, and now they need to keep looking. What we can hope to do is to hone down the area where they look next to maximise the chance that they find it as quickly as they can. Thanks, Lynn.
More questions? In the front here.
You mentioned the Great Expression project, and they want you to make a difference, and you know, being an academic who wants to make a difference. What barriers do you see there being to translating your research into systems, like operational systems, at scale, well made?
What barriers do I see? Yeah. Okay, so getting technology adopted, I think, requires a whole host of different skills, and I don't think a university on its own or a company on its own, be it a new one or a pre-existing one, or a government organisation on its own, is well placed to do it in isolation of everything else. So I think the biggest barrier is establishing the human-to-human interactions. That means that everybody in that ecosystem trusts one another well enough to fight through the tactical barriers that will inevitably occur, and seeing the strategic gain and merit in actually shooting for the end goal. So for me, that's an issue of interpersonal interactions, and in some sense is why I'm so pleased that there are so many people representing those different communities here today.
Something which we're about to do. Anthony.
Simon, standing letter. You're surprised to hear from a sense of biology I'm interested in whether your algorithms can be used to tackle big data biological questions. You've shown CR data, but what about really complex biology?
Yeah, so trying to think what exactly the status of the current project that I'm thinking of is. There is a likely future project, let's put it that way, which is explicitly looking at taking the algorithms I've been talking about and looking at them in a drug discovery context, where it is critical to have full understanding of the prior knowledge, but also, which I didn't really stress, full transparency of why it is you have reached the conclusion. And simply saying the computer says this isn't good enough. Nobody will be able to take that forward. Explaining what the correlation that you've identified is caused by, and at least what it might be caused by and what it might not be caused by, can dramatically help the ability to get those advances turn into actual biomedical product and therefore better human lives.
There's a question over there in the corner.
I think that's the algorithm, but it's what's it? Is it to sort particles quicker really when you run through the cycle than the particle field?
Yeah, sorry, I glossed over that. I was getting conscious I was overrunning in terms of time. So thanks, John, for asking the question. So when you run this particle filter thing, each of the particles can run independently of one another. So you've got one guess assessing the data, another guess sat next door to it assessing the data, and they get weights, and these weights get bigger and smaller as the data comes in. But there comes a point where you realise that some of the particles have a really big weight and some of them have a really low weight, and you want to get rid of the ones that have a low weight and replicate the ones that have a really high weight, and that requires you to perform this routing problem, which is what the patent relates to. Yeah, probably.
Question at the front.
Yeah, really nice. Simon, thanks for that. And you highlighted that difference in view between the model-based community and the database community, and your desire to bring it together and to reap benefits of understanding prior. So, what's the way forward? How do we tap into that knowledge that you have and bring that? Because the artificial community is off on a
yeah, the train is leaving the platform very, very quickly. Yep. So I think there's a twofold tactic. So which at least we're adopting. So one is that we identify specific niches where there is a clear resonance of articulating the benefit in that context. So two hats, right? And that's not straightforward, but I see it as straightforward to formulate the plan as to what to do. So that executing the plan may be challenging, but it is clear to me what the plan should be. The harder task is to do it generically once, to make a general purpose. One of the advantages of deep learning is you can throw it at any data set, and it's the same deep learning algorithm that you can reapply and reapply and reapply and reapply. And doing that, having software that embodies the principle is harder. My best guess as to how to turn that into something that is adopted is to embrace things called probabilistic programming languages, exemplified by STAN, which we've worked with, as you'll be aware, and to then bring that to the masses. But that is both difficult to do in terms of the much more challenging algorithmically, because you have to do something that is repurposable, but also challenging just in terms of the mechanics of how to engage with an open source community in a way that gets us to where I would like the world to be, particularly if not everybody in that community subscribes to that point of view.
I think we do have a question online.
Cool.
Filters require smooth parameter spaces in Bayesian context.
Do they require smooth?
Yes, smooth parameter spaces in Bayesian.
Yeah, sorry. Hi, Brett. Thanks for joining. The simple answer is no. So the more complicated answer is it's much easier if the space is easier to navigate. So conceptually, to try to keep the rest of the audience on message. So if you imagine you're trying to explore a space and you know which way up is, it is a lot easier to find your way. If you don't know which way up is, your best strategy is to move around randomly and guess, essentially, and then see how well you do. Moving around randomly always works, it's just remarkably inefficient. So at the price of inefficiency, yes, you can handle things where you don't know where up is, and that I think Brett's describing as not smooth. Hope that answered the question, Brett.
Okay. Any final questions from the room? In which case, I just want to once again thank Simon for a totally fascinating lecture. Thank you, Simon. And we can now decant outside, I think, upstairs for some nibbles, some drinks, and for more discussion. So thank you all for coming and thank you.
Was even the team must go on just in case the family.